Um, okay, good morning, everybody. So today is the tutorial session for week 8. I'm going to go through the tutorial sheet number 8, which is this one. So as you can see, there are 7 questions. I will go through as many as I can, right, and give you the full solutions. Okay. And as usual, if you have questions, I'm sure you will have questions. Please use the chat room, right? Okay. All right, guys. I hope you are well. By the way, your your mark for quiz 7, I will send it shortly. Within the next 2 hours, you should get an email from me giving your mark, feedback, and the correct solution, and how the correct solution was obtained. Okay, so check for your email. Okay. All right, guys. So let's switch the camera. I've been having problems with the camera lately. So if you have issues like blurring or something, please let me know. I will try to adjust it. All right, I will start with question 7. I know you may not be able to see this clearly, but you can see it on your from the website, the course website, what the question is talking about. So basically, it says that an engineering firm manufactures a component that has a lifetime that is normally distributed with the standard deviation of 3.4, right? And you're choosing 9 components, and their average lifetime is 100.8. And the question is to find the 95% and the 98% confidence intervals. Okay, so let's see how we can do this. So this is question 7. Once again, please, if you cannot see the visualizer clearly, please give me a shout. Okay, I will try to adjust it. Okay. So in this question, the question says explicitly that the population standard deviation is known. So if you went through the review session that I did on Tuesday, the confidence interval that we need to use here is this one. All right, this is the confidence interval that we need to use. Okay, right, and because this is the confidence interval that corresponds to the population variance or the population standard deviation being known. Right, in this question, you're told that your sigma is the population standard deviation is 3.4, and you're told that the sample size is 9, and you're told that the sample mean is 100.8, right? So we are given all this, right? And we are asked to find the 95 and 98% confidence interval. So first of all, let's find the 95% confidence interval. So 100 times 1 minus alpha is 95, right? Which implies that 1 minus alpha is 0.95, yeah? Which implies that alpha is 0.05. So this guy here will be Z 0.975, right? And you can read this from the table for the normal distribution. In the video for week 8, I showed you how to read this from the normal table. So if you haven't watched the video, please do so ASAP. Okay. So if you read this off the normal table, this will be 1.96, right? So we got all the numbers that we need. So we go back to the formula and sub the numbers in. So you get 100.8 plus or minus 1.96 times 3.4 divided by the square root of 9. Okay, guys? So if you work this out using a calculator, you get the lower limit as 98.58, the upper limit as 103.02. So this is the 95% confidence interval for the mean lifetime of the component. Okay, is that clear, guys, so far? This formula, Neil, is from the review session that that we did on Monday this week. Is from, if you read the notes for week 8, Neil, you should go back to the website, and on Monday I talked about different confidence intervals for different situations. So this confidence interval is for the population mean when the population variance is known. So this is the formula I gave you on Monday. If you haven't watched the review session video, please, it's on the course website, Neil. So please go back and watch the video for the review session. All right, so this is one of the formulas I talked about. Okay, you just need to pick the right formula for the right situation, guys. Right, so in this case, since the population variance is known, this is the appropriate formula. Okay, any other questions, guys? Hello, guys, talk to me, please. Are you guys okay so far? Okay, then the second part of the question is to find the 98% confidence interval. So 100 times 1 minus alpha is 98. So your 1 minus alpha is 0.98. And so your alpha is 0.02. And your Z1 minus alpha by 2 will be Z 0.99, right? And if you read this off the table, again, if you haven't watched the video about how to read this off the table, please do so. Okay, this will be 3.26. All the videos are on the course website. I'm sure you guys know where the course website is, right? I showed you just a minute ago where it is, right? So this is the value that you will get if you read the normal table, all right? So once again, if you use this formula one more time, if you read this formula one more time, guys, you will get x bar, which is 100.8 plus or minus 2.326 multiplied by 3.4 divided by the square root of 9. Okay, right, and this, if you work it out, this will be the lower limit will be 98.16. The upper limit will be 103.44. So this is the 98% confidence interval for the mean lifetime of the component. All right, guys. Yes. Are you okay, guys, so far? So this is the solution for question number 7 on the tutorial sheet. Tutorial sheet 8. Are you any questions, please? I mean, I really want you to do well in this course. So any simple question or hard question, please let me know. All right. Okay. All right. So let's go back to the tutorial sheet. The next question is question. So I'm done with question 7. The next is question 6. So here you have a chemical concentration in a fish caught in Lake Michigan in the US. And it says that the standard deviation of the concentration level is 0.8 parts per million. And you're choosing a sample size of 10, and these are the data that you get, right? And the question is to find the 95% and the 99% confidence intervals. So let's see how we can do this. So once again, you need to figure out, this is question 6. You need to figure out which formula to use in this case, right? Remember, I gave you 4 different formulas on Monday this week. There was one formula for the population mean when the population variance is known. The second formula for the population mean when the population variance is not known. The third formula is for the population variance, and the fourth formula is for the population proportion. Now, of those 4 formulas, the one we need to use here is, what do you think it will be? Hello, guys. Which formula you think we need to use for question 6? Talk to me, guys. It will be the same as the one we used already, right? Because this is the formula that we just used. We need to use the same formula because if you read the question, it says explicitly that the standard deviation is 0.8. So in other words, that the population standard deviation is known and equal to 0.8. All right. Okay, so we need to so we are using the formula for the confidence interval for population mean when the standard deviation is known, which is this formula, right? Okay, so let's write down what is given to us. Sigma is 0.8. N is the sample size is 10. Now X bar is the sample mean. Now to compute X bar, you got all these 10 different data values, right? So X bar is simply the average of these numbers. So what you need to do is you need to take the sum of these 10 numbers and divide by 10. That will give you X bar. So if you do that, guys, you will get X bar to be 11.48. Okay. Now let's look at the 2 parts. The first part is to find the 95% confidence interval. So 100 times 1 minus alpha is 95. All right, so 1 minus alpha is 0.95. Your alpha is 0.05. And Z 1 minus alpha by 2 will be Z 0.975. And this will be 1.9. If you read it off the table, it will be 1.96. So using this formula one more time, using this formula, you will get 11.48 plus or minus 1.96 multiplied by sigma 0.8 divided by square root of n, which is 10. Right, so if you work this out, you will get the lower limit to be 10.99 and the upper limit to be 11.98. So this is the 95% confidence interval for the mean concentration level. Okay, guys? If you're not okay, please let me know, all right? I'm here to help you guys, okay? All right, the next confidence interval we are asked to find is the 99% confidence interval, all right? So So your 100 times 1 minus alpha is 99. Okay. So your 1 minus alpha is 0.99, and your alpha will be 0.01. Okay. So your z 1 minus alpha by 2 will be this, and if you work this out using the table, this will be 2.576. Excuse me, let me close the too many emails. Okay, so this is what you get. Now, if you sub this into the formula that I just mentioned, this one, all right, if you sub them into the formula, you will get the confidence interval to be this, right? And if you work this out, you get the lower limit to be 10.83, the upper limit to be 12.13. So this is the 99% confidence interval for the mean concentration level. Okay, are you guys okay with this? So this is the solution for question number 6 of the tutorial sheet. Talk to me, guys. Are you okay or not okay? Let me know. Hello, guys. Are you okay so far? Any questions? Please let me know. Okay, thank you. All right. So the next question I'm done with question 6. So the next question is question 5. What it says is that you have a random sample from a geometric distribution with unknown parameter p. The first part is to write down the likelihood and the log likelihood. And the second part is to find the maximum likelihood estimator for p. All right, so let me show you how to do this. I think I did this question before, but anyway, I will do it again. So this is question 5. So the first thing you need to do is to write down the likelihood function, right? I mean, I did many questions. I think over 20 questions I did on maximum likelihood estimation. So the first thing to do is the product I from 1 to n of the density function, in this case the probability mass function of the geometric distribution. So, okay, so this is what you have, right? Now if you take the product of this, there are two terms. You see, this is the product of the p first, then the product of okay. All right, now the product of p is a constant, right? So the product of that is p power n, and the product of this guy here is, remember, I think I mentioned this before, there is if you go to the preliminary section of the website, there are formulas for simplifying products of terms. And those formulas are really useful, especially when you come to MLE questions, questions on maximum likelihood, right? So please, if you haven't seen it, please go to the preliminary section of the course website, and there is a video on, I think the title of the video is something like properties of product, or something like that. Yeah. So please watch that video, and that will really help you to do the questions on MLE, right? Okay. Okay. Now this you can simplify further to if you take the summation inside, you get the sum of xi, I from 1 to n, and minus, you take the sum of 1. Sum of 1, I from 1 to n is n, right? Okay, so this is what you get. All right, the next thing to do is to take the log of the likelihood function, right? So that will be n times log of p, yeah, plus the log of this term will be okay. All right. Okay, so that's the first part. Now the second part is to find the MLE. Okay, I'm sure all of you know that to find the MLE, what you need to do now is to take the derivative of this with respect to p and set it to 0, and then solve for p. So that's what I'm going to do now. So I'm going to take the derivative with respect to p. That will give you this, right? And you set this to 0, and I'm going to solve for p, right? So now this implies that n divided by p is equal to this, right? Now, if you do cross multiplication like this, you will get n minus np equal to p times yeah, and these two terms cancel out. Okay, so your p, or the solution for p, let me call it p hat, is gonna be n divided by the sum of xi. Okay, and this you can write this as 1 divided by the sample mean. Okay, so this is the solution for this equation. Now, to make sure that this is an MLE, you need to take the second order derivative with respect to p. So that's what I'm going to do now. So let me move to the next page. I mean, okay. All right, just a minute, please. Just a minute. Okay, so I mean, please let me know if anything not clear. So what I'm going to do here is I'm going to take the second order derivative with respect to p. So that's going to be the first order derivative of this, right? So it's going to be n minus n over p squared minus okay. Okay, so this is a 2, guys. Okay, now this this term here is clearly negative. This term is also, I mean, it's also negative, but we need to make sure about the sign of this. We need to make sure what values this can take. That is sum of xi minus n. Now, in order to see that, you know that xi is a data value from a geometric distribution. So by definition, it must be greater than or equal to 1. Okay, because this is a data from a geometric variable, and the geometric variable, the minimum value it can take is 1, right? So xi must be greater than or equal to 1 for all I, right? Now this implies okay, all right, and this implies now sum of 1 I from 1 to n is n, right? And this implies further that okay, all right, so we have shown that the value of sum of xi minus n has to be non-negative. So in other words, this term here is non-negative. So you have a negative sign in front of it, and you also have a negative term over here. So that means that this has to be less than 0, right? So hence we have shown that p hat equal to 1 over x bar is the MLE. All right, guys, is this clear or it's not clear? Please let me know. Some of you may find this boring because I've done so many questions on MLE before. Are you guys okay with this or not? Hello, guys, talk to me. So this is, are you okay with question 5? Yeah, thank you. All right. So let me move to the next question. So I just finished doing question number 5. The next question I'm going to do is question 4. Question 4 is this one. I don't know if you can't read this, please read it from the course website. Okay. It says basically that you have 5 data points, a random sample from a binomial distribution with parameters 3 and p. The first part is to write down the likelihood function, and the second part is to find the MLE. Okay. All right. So let me show you how to do this. So this is question number 4, part 1. Okay. So we have 5 data points, I from 1 to 5, each coming from a binomial distribution with parameters 3 and p. Now you may recall, I'm sure you know from probability 1, the PMF of a binomial is there, yeah. So this becomes Okay, all right. Now let's try to simplify each of these, right? So the first term you can't simplify. You just cannot simplify this. So you have to write it like what it is right now. Now the second term here, you can you can simplify this to the following. Okay. And the third term you can simplify to this, right? Okay. And further, you can write just one more step. All right. Now you should take the sum inside the brackets. All right. The sum of 3 is 15, right? And the sum of xi is just simply sum of xi. All right, so this completes part 1 of question number 4. Now part 2 of question 4 is asking you to find the MLE, and you are given the data. You are given the data for the x's as follows: 1, 3, 2, 2, 3. All right, and so for that data set, you are given the data set. Okay, let me write it down. The data set is this. You have x1 equal to 1, x2 equal to 3, x3 equal to 2, x4 equal to 2, and x5 is equal to 3. All right, so these are the data set that are given to you guys. Okay. And given this data, we need to work out the likelihood first. All right, so the first thing is that you need to work out the sum of the data. So if you take the sum of these values, 1 plus 3 plus 2 plus 2 plus 3, that gives you 11, right? Okay. So LFP, the likelihood becomes as follows. Okay. And then P to the power, the sum of xi, which is 11, and 1 minus P power 15 minus 11, right? This is what you get. Now, if you simplify this using a calculator, you will get 27 p power 11, 1 minus p power 4. So this is the likelihood function for the given data set, right? Okay. All right. The next thing we are told is the following, that we are told that the possible values for p can be one of these, either 0.5, 0.6, 0.7, or 0.8. The question is, which of these is the MLE, right? Now, to answer that question, you need to create a table, okay? And the first column will contain the possible values for P, which is 0.5, 0.6, 0.7, or 0.8, right? And this column will give you the likelihood values So when P is 0.5, if you sub here 0.5, you will get the likelihood to be equal to the following. 8.24 times 10 to the power minus 4. When P is 0.6, you get 2.51 times 10 to the power minus 3. When P is 0.7, you get 4.32 times 10 to the power minus 3. When P is 0.8, you get 3.71 times 10 to the power minus 3. Okay, guys, so these are the likelihood values corresponding to the 4 different values for P. Now the question is, which is the MLE? Remember, the maximum likelihood estimation says the MLE is the parameter value for which the likelihood is the largest. So in this case, which one is the largest? The largest is this guy here, right? This is the largest of the 4 likelihood values. So the MLE, hence, all right, the MLE is 0.7, all right, because 0.7 corresponds to the largest likelihood value. Okay, guys, so this is the solution to question 4 of the tutorial sheet. Are you okay with this or no? Hello, guys, talk to me. Any questions, please feel free. Please feel free to ask me. Are you guys okay? Hello? All of you okay? All right. All right, so let me go to the next question on the tutorial sheet. I'm working backwards if you just joined me. So I'm done with question number 4. The next question I'm going to look at is question 3. So here we have a random sample from this PDF. The first part is to show that X bar is a sample mean, is a biased estimator of delta. All right, so let's see how we can do this. So this is, I may not have time to I don't know, I will try my best. This is question 3, part 1. All right, and you have given the estimate X bar is, you're told that X bar is an estimator of delta, right? Okay, now you are asked to show that there is a biased estimator. All right, so what you need to show is that the bias of X bar is not equal to 0, right? So you need to show whatever this works out to be is a number that is different from 0. Now remember, the bias is defined as this. This is the definition of bias. So this is right. Now take the expectation inside, you get 1 over n times the sum of the expectation of xi minus delta. Now to find the expectation of xi, I'm gonna integrate the density function, which is given by this, right? So it's basically 1 over n integral from delta to infinity of x e minus x plus delta dx minus delta. Okay. You guys with me so far? Now, the delta is a constant, so you can pull it outside, so it becomes like this. Okay, guys. Now, how do we do this integration, guys? I'm sure you know calculus more than I do. To do this integration, you can do it in several ways, but one way to do this is to use integration by parts. So that's what I'm going to use. So I'm going to use integration by parts, right? So you get, so if you do that, okay, you get this. Right? All right, now let's take the limits. So this will be the limit at infinity will be 0. The limit at delta is minus delta E minus delta, right? And the integral of this is not difficult, so it's simply minus of E of minus x. Take the limits from delta to infinity. Okay. So this will be some, this is delta E minus delta. The limit at infinity is 0. The limit at delta is minus E minus delta. Okay, like this. Take away this, right? All right, the next step, I'm going to bring the, you see, you got this term outside. I'm going to bring this inside the brackets, right? So if you do that, you will get 1 over n times the sum of delta plus 1 minus delta. You see how this comes about. You see, what I have done is to multiply each of these terms, this one and this one, by e to the power delta. So you get delta. If you multiply this by this, you get delta. If you multiply this by this, you get plus 1. Okay. All right. So this becomes 1 over n. This is a constant, so it's going to be n times the constant minus delta, right? So this is going to be delta plus 1 minus delta, which is equal to 1, which is not equal to 0. So hence we have shown that the bias of x bar is a number that is different from 0, right? So the conclusion is that x bar is a biased estimator of delta. Are you guys okay with this? I mean, it looks like a long series of calculations, but it's not really hard because I mean, this is stuff you have done in your calculus course in semester 1. So it's not, it shouldn't be difficult for you. Are you okay, guys, so far or no? Any questions? Hello, guys. Hello, talk to me, please. Are you okay? All right. So that's the first part of question number 3. The second part of question number 3 is, so this is question 3, part 2, is asking you for the bias, which we have already found out. the bias is equal to delta. And it's also asking you what happens to the bias as n goes to infinity. This is 1, guys, right? As n goes to infinity, the limit of 1 as n goes to infinity is 1, because 1 is a constant. It doesn't depend on n. All right, so the limit is also equal to 1. Right, and finally, the last part of question 3 is asking you, can you derive an unbiased estimator? Remember, an unbiased estimator is an estimator with the bias equal to 0. Now, if you look at part 1, we got the bias of x bar to be equal to 1. Now, if you want this to be 0, all right, what you need to do is to simply take away 1. Instead of considering the bias of x bar, you look at the bias of x bar, take away 1. Then this guy here will become 1 minus 1, which is 0. All right, so to answer this question, in order to answer part 3, all you have to do is define a new estimator. Let's call it delta hat, which is x bar minus 1. All right. Okay, and then the bias of delta hat will be the expectation of delta hat minus delta, which is the expectation of x bar minus 1 minus delta, and this is the expectation of x bar minus 1 minus delta. And from part 1 of question 3, we know that this guy is delta plus 1. So this is 0. All right, so hence we have shown, x bar, delta hat, right, is an unbiased estimator of delta. All right, remember, if the bias is 0, then the estimator is said to be unbiased. All right, guys, so this completes question number 3 of the tutorial sheet. Are you guys okay with this or no? Hello, guys. Hello, talk to me, guys. Are you okay or not? Thank you. All right, so I've just finished question 3. There are 2 questions left. I don't think I run out of the. I don't have the time to do question 1 or 2, but I will post the full solutions to all the 7 questions later today in the course website. So if you go to the course website later today, you will be able to see the typed solutions, the handwritten solutions, as well as the video solutions for all the 7 questions in this tutorial sheet. All right, guys. So I hope you have a good day today, good morning or good afternoon, and I will talk to you later, guys. So have a good day, and as usual, any questions you guys have on this course, please feel free to contact me 24/7 by email, Skype, Zoom, or phone. My phone number is, I'm sure you know, is 0161-273-2941. All right, guys, so take care of yourself and have a great day. Okay. The last page, yeah, this is the last page, sir. This is the last page.